for the last question of 6.5, the last question of chapter 6, actually, we have question number 3. A 500 Newton crate is resting on a ramp. The ramp is inclined 8 degrees counterclockwise from the horizontal. So we will draw that just to get a better visual in our heads. So it wants us to resolve the weight into 2 rectangular components, meaning I want the horizontal component of that vector and I want the vertical component. So one that's parallel to the ramp and the other is perpendicular to the ramp. So first, the object is resting on a ramp, right? So the crate is already slanted. Our components need to be drawn based on that original state. So what I'm going to do is draw my ramp. Just quickly. Again, 8-degree ramp would be something very small like that, but then I couldn't really draw in it. So I'm just going to make it a little bit bigger, but just know that it's only bigger for like demonstration purposes here, right? But normally that angle would be smaller. So here is my ramp. And my crate. Let's draw my crate. It's just resting on the ramp, it says. So something like this. There's my crate. I'm just going to put a C in it because I don't think I can put the full word crate in there. I can't write that small. So a 500 Newton crate. So what forces are acting on the object? So I have the force of gravity, right? Which is downwards, which is 500 Newtons. So let's draw that in. So from the crate, I have a downward, directly downward force of gravity, which is 500 Newtons. The resultant vector, right, is the exact opposite of this force vector since the object isn't moving. So because it isn't moving, we know that I would have a 0 vector, which means I would have a resultant vector exactly the opposite of this force vector. So let's draw that in. I'll draw it the same color. So then I have, I'm just gonna go a resultant vector that's also 500 Newtons, right, upwards. This is our starting point there. There's also a force parallel to the ramp, it says, if we think about it. The crate isn't sliding. It's on an angle on the ramp. So not only gravity, but in terms of like horizontally, the crate is not sliding. So we also have the force of friction at play here, right? There's some grit on it to not make it slide down. So let's draw in the force of friction. So normally it would be, I'm going to do that in a different color. Normally, if it was going to slide, it'd be sliding in this direction. So you've got your force going in the opposite direction, parallel to the ramp. So I'm trying to draw this vector in parallel to my ramp. Okay. And there is also another force that's perpendicular to the ramp. So what is the force that's perpendicular to the ramp? So we call that actually the normal force in math. So let's draw in our perpendicular to the ramp. So perpendicular to the ramp would also be perpendicular to this friction vector, right? So just trying to draw 90 degrees from there. Like that, let's say, right? That looks like about maybe a bit straighter, closer to the vertical, about like that. And this is perpendicular to the ramp. Perpendicular to the ramp. And so this would be 90. But I'm going to redraw this. This would be 90 in here, right? So I also should write in my orange that is my force of friction vector. So this orange, this is my force of friction. So why don't we call it vector F, your force vector, and subscript F, right? Because it's your friction vector, let's say. And let me just also make note here that my original horizontal component and my vertical component vectors. So my horizontal component in this case would be equivalent to the friction vector, right? And my vertical vector now, because things are slanted, would be equivalent to my perpendicular one, but we'll call it, we said it was a normal force. So my normal force, these are the variables I'll be using now, right? So let's redraw this. I'll go over here. So we need to draw our horizontal and vertical component in, right? First, I need a vertical. I need my resultant vector. So I have been doing it in red. So let's do just this top part, my resultant vector in red. Let's say starting at the origin here and coming up. And that is my resultant vector, and that would be 500 newtons of force. Then I need my force of friction. So let's go back to orange. And that vector is at 8 degrees, right? Because again, this vector here is parallel to the ramp. The ramp is at an angle of 8 degrees. So I'm going to draw it in at an angle of 8 degrees, which again is very small. It would be like this probably. I'll go just a little bit higher, and it's not a very strong force, so it's not going to be a very long vector. And I want those heads to match up, right? So that's how I'm looking how long I want it to be. So when I draw my rectangle, these line up basically. And let's label that as my force of friction vector. And also that this angle here is 8 degrees, right? Same as the ramp. And then in green, I will put my perpendicular vector, which would be my normal force vector. So draw it perpendicular. Hopefully I'll do an okay job. So I'm kind of going like this, but I have to start here. And so that those would line up to make a rectangle basically. That doesn't look too bad. And again, if this is representing horizontal, this is vertical, it would be 90 degrees in the center. And then let me label that vector. So I have my normal force vector, which is perpendicular to the ramp. I have my resultant vector, the opposite force, causing the object not to move, and I have my friction vector there. So what other information can I put in? I have 8 degrees here. Let me finish my rectangle. I usually have been doing that in black. So let's just say if I was finishing my rectangle here, right? It is a rectangle, so I can put 90 degrees just so we know on all the corners. You don't have to if it's going to again mess up your drawing there, then, but just so you know that it's 90 degrees in all the corners. So I have 8 degrees there. Let's say I don't know, I have 90 degrees here. I don't know the inside here, but I can figure it out, right? Because again, if this is directly vertical and horizontal, that's 90 degrees. So 90 minus 8, right, would be 82 degrees. And I've got my one side, right? This is my normal force vector, which is also the same on the opposite side, whether you'd need to write that in. And then my friction vector would be the same at the top here. So because depending, I'm thinking, you know, you would write it in here if you're choosing this triangle. You would write this in on this side if you're choosing this triangle. So either way, you have to write one of them in, right? So again, I have one of the sides, if that's 90 degrees, the hypotenuse, if I chose this triangle, 90 degrees, that would be the hypotenuse side. I'm trying to figure out the other sides, the horizontal and vertical side. And so how many angles can I get? I've got 90, I have 8, I have 82. So let's say here, how was I? If that's 8, oh, if this angle here is 90, right? If this angle there is 90 and this is 82, then what's left over of 82 to get the rest of the angle? If the entire angle is 90, that would mean that this angle in here is 8 degrees as well, this angle here. If we look at that as our theta, let's say. So let's say I chose this triangle, I have 8 degrees, I have 90 degrees. I could figure out this angle here. Let's see if we need to. And I have one side and I need to figure out the other sides, right? So I only have one formula for each. Because I have 90 degrees, those formulas will work. So let's see what we can do first. We usually use cos, let's say the formula first, though it really doesn't matter, right? I'm just going in that order for no reason. So if I was to use cos of 8 degrees, right, would be adjacent. Adjacent to me would be my normal vector over my hypotenuse. So we're going to figure out the normal force first. And again, the normal force is really the vertical component. So my vertical component is equal to adjacent over hypotenuse, which is cos. So I have the cos of 8 degrees. Cos of 8 degrees is adjacent my normal force over hypotenuse is 500. So my normal force is equal to 500 in front, right? The number in front multiplied by cos of 8 degrees. So 500 cos of 8, 495.1 newtons. And so then I know if I do the sine that I would get the opposite one, right? So then if I got the sine of 8 degrees, let's just stand there and do the sine would be opposite. So that's my friction vector. So I'm figuring out the magnitude of my friction force over, again, opposite over hypotenuse, that 500 again. So then to figure out that horizontal vector, because the friction vector is the same, we're saying is equivalent to what I would have figured out as my horizontal component, would be 500 times sine of 8 degrees is equal to my horizontal component or friction force. So 500 times sine of 8 degrees, I have 69.6 newtons. And you can also see that the orange vector, the friction vector, is shorter than the normal force vector. And again, the friction vector here is smaller in value in force than my normal force vector, than my perpendicular vector. So let's write down that which is which here in terms of the original question. Resolve the weight into two rectangular components, one that's parallel to the ramp. So the one that was parallel to the ramp, right, is my friction vector. So I should write that down here. This one is the one that is parallel to the ramp. And I can put that in a therefore statement, right? Therefore, the component parallel to the ramp would have a force of 69.6 newtons. And the vertical component perpendicular to the ramp would have a force of 495.1 newtons, for example. So perpendicular to the ramp, right, is my normal force. And that one would be right here, my normal force vector. So let's write down that that one's perpendicular to the ramp. Perpendicular to the ramp.